This is problem 18 of the QHack 2023 Quantum Coding Challenges, and this one is entitled The Itch to Switch. And in this problem, we're told that two parties, Zenda and Reese, want to take a classical state, so in this case, this J is only state either 0 or 1, and this K is also state either 0 or 1, and they want to copy it from one qubit to another. Now, this is a very simple thing to do, right? If we wanted to just take this state 0 or 1 and transfer it to this qubit here at the output, all we would need to do is just apply a CX gate with control on this qubit and target on that qubit, and that one initialize at 0. But the restriction here is that we are not allowed to do direct operations between this qubit and the one where we want to transfer it to, and same for this qubit J. We cannot apply any control gates from this qubit down here to where we want to copy that qubit to. What we're told is that we can apply operations between those states that we want to copy and qubits where we have a bell pair. So these two qubits are entangled and they share a bell pair. And then we can perform some other operation here to, for example, swap them from this qubit to the other. Now this problem seems complicated because we see here a lot of different blocks, but what makes it really simple is the fact that what we're trying to copy are classical qubits. And if you start looking at this problem hard enough, you will notice that this is almost identical to a similar problem we covered already, which is superdense coding. So if you go back to problem 15, I believe it was, which was entitled sub-superdense coding, we reviewed the superdense coding protocol, which I have a simplified circuit of that here. So if we look at this again, what we have is, two parties, Alice and Bob, and they create a bell pair, right? So they entangle their qubits, and then Alice encodes classical bits into either applying an X gate or a Z gate, and then by applying the reverse of that circuit that generates the bell pair, we can basically transfer two classical qubits by using only one qubit, this one right here, which is shared between Alice and Bob. Now, in this problem, if you take a close look at this scheme for superdense coding, what you will notice is that because we're told that the qubits we want to transfer can only take the classical states 0 and 1, this is almost identical to what we had before. So if I take this qubit, this classical bit I, and just move it to the bottom, and now I call it K, just because this is what we're told in this problem, then here at the top, we can see that we have this same CX gate between this J and this qubit, right? And now at the bottom, this Z gate is not being applied to the same qubit, it's being applied to the other qubit, but because the application of a phase change to a bell pair affects both qubits simultaneously, it doesn't matter if the Z gate is applied here or down here, it would create that phase change. So this problem is actually, even though it's supposed to be one of the hardest ones, which is valued at 500 points, it's actually extremely simple. All we need to do is realize that because this qubits can only take classical states, it's almost identical as the superdense coding protocol. So that's it. All we need to do is just implement this circuit in PennyLane. So let's go ahead and do that. So as always, we import PennyLane as QML and then NumPy. And then we're just going to create a Q node with the wires of interest. So Zenda's wires and Reese's wires. And then we generate that bell pair between the two of them. Then we apply that CNO gate between Zenda's qubits and that control Z gate between Risa's qubits. And then we do the reverse operation of generating the bell pair. Now here in this problem, we are told that we're going to be given the J and K values, and we need to encode them in the form of some input basis state. So we just basically need to make sure we encode those two so that we are, generating either 0 or 1 in this J and K here at the input. And then we just need to return the probabilities of all wires. So then let's go ahead and draw our circuit for example, J equal to 1 and K equal to 0. So here we have the circuit that entangles or generates that bell pair, then the embedding of the 1 for Zenda and the 0 for Ries, that CX gate between Zenda's qubits and that CZ gate, control Z gate between Risa's qubits, and then that CX gate and Hadamard at the output. Now, it would seem a little bit clearer if I put this basis embedding at the beginning, right? So it matches better this circuit, but the idea is the same. And now to check our output, let's just evaluate our circuit. And here what we can do is try, if we input 0, 0, we should get all zeros at the output. So here we have it, we have all zeros at the output as a 0 state. Now if we input here 0, 1, we should get 1, 0, 1, 0. So in penny lane, this is the most significant bit. So that would be 0, 1, 0, 1, which is 5. So if we do that, we get 0, 1, 2, 3, 4, 5. So let's stay 5. If we do 1, 0, then we should get 0, 1, 0, 1. So that's 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And if we get, if we input 1, 1, we should get all ones, which is state 15, right? So here we have it, we get state 15, and that shows that our circuit is working correctly. We can effectively copy this qubit Z0 to R1 and this qubit R0 to Z1. Again, if you have any questions, let me know.